All right, so today we're going to look at what makes a relation a function and what keeps a relation from being a function. All right, on page 155, it says a set is a collection of items called elements. So a function pairs each element in one set, and we call that first set the domain, with exactly one element in the second set. And we call that second set the range. So a function pairs each element in the domain with exactly one element in the range. Here we have an example, and this example is given to us as a mapping. Here we have our domain, and the elements in our domain are 0, 1, 2, 3, and 4. And here we have our range. The elements in our range are 0, 1, 4, 9, and 16. Now this example is a function because the 0 is paired with only one element in the range. The 1 is paired with only one element. The 2 is paired with only one element. The 3 is paired with only one element. The 4 is paired with only one element. So let me give you another mapping. Okay, let's do 2, 4, 6, 8, 10. I'm going to have 2 paired with 6 and 4 paired with 8 and 10. Is that a function? No, it is not a function. Because the element of the domain, one element of the domain is paired with more than one element of the range. Okay, now let's look at this. 2, 4, 6, 8, 10. Is that a function?
Yes.
Yes, because the 2 is only paired with one element, the 4 is only paired with one element, and the 6 is only paired with one element. So yes, this is a function. Okay, a function can be described using function notation. Now usually when we talk about domain and range, the domain we say is the input. And what do we usually use to describe the input? X is generally used. Okay, the range is our output. And what have we always used for the output? Y. Okay, so usually we would call our input X and our output Y. But now we're going to start using function notation. And instead of using X and Y, we're going to say the function f assigns the output f of x. So our output is going to be called f of x in the range to the corresponding input of x. So if I input 0, what do I output? 0. If I input 1, what do I output? 1. So if I said f of 3, if I input 3, what is my output? 9. What is f of 4? If I input 4, what do I get out? 16. Now.
So you're basically squaring them?
Ooh, that was the next question. Can you tell what I'm doing to the input to get the output? I am squaring the input to give me the output. And now I've written the model for this function. To find f of x, all you do is square x. Square the input to get the output. So what would f of 10 be? 100. If we use that rule. Does that make sense? Okay. Now we're going to look at this reflection down here at the bottom. Since the domain of that function above, the one we just looked at the mapping, can be written in set notation. So this domain includes the elements, and we would use braces. See how they have the brace at the end? 0, 1, 2, 3, and 4. And they're asking us to write the range in set notation. So the range contains what elements? Wait, did it contain 0? Yes, it did. Okay. So 0. What else was in the range? 1, 4, 9, and 16. Okay, so this is written as a set. Our domain is described this way. And whenever we have discrete data, when it's not continuous, when it's discrete, we would write the domain and range as the sets here. That was lightning for those of you that were hoping that you don't have to practice the sport outside. It's looking good for you. All right. Doesn't mean you won't practice inside. All right. B. Tell how the statement f of 4 equals 16. And guys, do you see how I said that? F of 4 equals 16. So this is how we would read it. F of 4 equals 16. Yes, sir.
So basically you can just say f is like square, so square of 4 equals 16.
F is what we named this function. Now, all functions are not called f. We can pick any letter we wanted to name a function. I can call it function G, or function H, or function T, or function A. We can call it function anything. Well, not anything, because we're in school. We have to do proper. Okay? But we can label them with multiple letters. So, it's not always f of x. It might be g of x equals something, or h of x equals. And it's not always x. We don't always label our input x. Sometimes we might do it with respect to time. So it might be d of t, distance with respect to time. Okay?
You still square it though.
In this case we square it, yes, but it's not always squared. We can have lots of different relationships that give us functions. This one did, and we're going to look at a lot of different others that also do. Now, this f of x does not mean, see it says right here, it does not indicate that we're multiplying. This is just function notation. This is not f times x. This is f of x, which means I am plugging the independent variable x into the function f and getting an output. That's what this means. Okay. So, when you plug 4 into the function f, you get out 16. That's what f of 4 equals 16 means. When I plugged 4 into the function that I called f, I got out 16. That's what this statement means. That's what this means. When I plugged 4 into the function f, I got out 16. Okay? Alright, now this says suppose 3 were paired with 4 instead of 9. So let's go back and look and see what that would give us. 3 with 4, so I'm going to change the color to blue here so we can see there's a difference, instead of 9. And I'm going to make this go away. Okay, so now we have 3 paired with 4 instead of 9. It's like Moby Whiteout. Alright, if this scenario happened, is this relation still a function?
No. Yes.
Yes.
Yes. Okay? So, would this still be a function? Yes. Because each element of the domain is paired with only, whoops, I left out the word with, one element of the range. Okay. Now, this one's different. This says suppose the 3 were paired with the 4 and the 9. So let's go back and look at the picture. Now we're with 4 and 9. Is this scenario a function?
No.
No. And the reason it is not a function is because 3 is paired with more than one output. Okay? Because 3, which is an element of our domain, we have an input that is paired with more than one output. And therefore, it's no longer a function. Okay. Now, I want you to think about this one for just a second. Don't answer out loud until I tell you to. If you pair each month, January, February, each month, with all the possible number of days in that month, will you get a function? Don't say it out loud. Just think about it. Okay. Now that you've thought about it, how many people think yes? How many people think no? Okay. I like the mob mentality. This is good. No is right. Why is it no? Who can tell me? Hey, Rose?
Because each month has a 0, 28 or 31, but there's still like 1 through at least 28 would still be every month would still be paired with that one, and you can't have it again.
Okay, well, January is only paired with 31. But Ian, what happens with February?
Leap year.
February can be paired with what?
28 and
28 and 29. So February is our 1 month that keeps this from being a function. February blew it for us. We've got leap year that gives us 2 options for the number of days in a month. Okay. Is that what you were getting to?
Like, wouldn't it also have like all
That's
the
not what you were
questions?
thinking. Okay. Ma'am?
Like, wouldn't it go with all the other ones? I thought it meant like 1, 2, 3,
Yeah,
4,
that's what I
5.
thought.
Yeah, I thought the domain was 1
Yeah.
through 12,
Okay.
and then the...
Sure. We can do it like that. Let's say the domain was 1 through 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh man. 11, 12. Alright, there we go.
And I thought the range was 1.
And the range would be
1 through 31.
all the possible number of days in the month.
So 1 through 28.
No, it's 28 to 31.
No, it's
No, it'd be
31
1
months,
through
1.
Okay, I see how you interpreted the problem. Okay, this is what it should have been.
So then, but then we thought that
Yeah,
like 1
gotcha.
would go with
Gotcha.
all of those,
Yeah.
and 2 would go with all of
Okay.
those, 28.
Alright.
There can't be possibly.
I think this is what they were indicating. This would be your other one, and what kills it is that the 2 goes here and here. Because every other input is just paired with 1
The
output.
question was pretty vague, so...
I think
Yeah.
they
Oh,
meant
I liked it.
all the
I really liked it.
like.
Okay, let's flip over to the next page on page 156. And they're linking us back to what we learned in science. Since functions are often used to describe relationships between 2 variables, and we do that in mathematics, and we also do it in science. In science, you always have your independent and your dependent variables. Did y'all study that in middle school? Yes. Okay, so the independent represents the input value, and the dependent represents the output. So for us, the independent values end up being our domain, and the dependent values end up being our range. Okay? Now, a lot of times we can write a function rule, and we did that just a minute ago. I think Ian came up with a function rule for us this class. He said this is the function rule. F of x equals x squared. for this particular function, this is our rule. But we have lots of functions, and we'll have lots of different rules for our functions. Now, we can't always write it as a nice simple equation like we just did. Sometimes it's an equation that has multiple parts to it, a piecewise. But we can write function rules for many of our functions, and here's one you're very familiar with. Y equals mx plus b. This is a rule that you have used over and over and over again. So today we're going to look at this y equals mx plus b, but we're going to think about it in terms of a function, because this is a linear function. And so basically for you, and this is probably what your brain's going, okay, the y turns into an f of x. Yeah. That's what's happening. You already knew about input and output. Now we're just defining it in terms of a function. So yeah, that's what's happening. Y changes to f of x, or g of x, or h of x, or, you know. Alright, let's take a look at these and see if we can just tell whether each pairing describes a function. So the set of whole numbers 1 to 9 are paired with its opposites. Is each input paired with exactly one output?
Yeah.
Yeah, because you can only have one
No.
output.
Yes.
There is no, yeah, right. There's no negative zero. So zero is zero.
Well, 0 is still 0, so it's not like it's paired with more than one thing.
Zero doesn't have an opposite.
All of it,
Zero's all
0, 0.
Yeah.
That's confusing, but it's the same.
Okay, I agree. What if this had said 1 to 9? Would we be good?
Yes.
Okay.
It's still, 0 is still a number, though.
0 is a number, but the opposite of 0 would just be considered 0. It doesn't have an opposite. So it would only be paired with one element. So still, it would only be paired with one element. So we could say yes, but I understand your confusion with 0. Okay. Alright, this one, whole numbers 10 to 12 paired with their factors. So let's think about what are the factors of 10. 1 is a factor of 10.
5 and 2.
5 and 2 are factors of 10. And so if I broke 10 down, these are its factors.
Definitely no.
Okay, and even numbers 2 to 10 paired with half their number.
It's like 2
So 2, 4, 6, 8, 10 paired with half. 1, 2, 3, 4, 5. And I'm writing all of these as mappings, but we certainly wouldn't have to. Let's do one as a table. Let's just turn it into a table. So 2, 4, 6, 8, 10. Is this relationship a function?
Yeah.
Yes. Can we write a function rule for that?
Mm-hmm.
Yeah? What do we do to our input?
Half it.
Divide it by 2. Half it. There's our function rule for that function. Okay, is number 5 a function?
Nope.
Nope. What's wrong?
X is repeat.
Okay, I'm glad you said that. When we look at a set of ordered pairs, you may have been taught to determine if it's a function, see if your x's repeat. Okay, so that is what we can look for. So we see that 36 is paired with 6, and 36 is also paired with negative 6. So we know our answer is no. But if we had to explain why, an explanation is not that the x's repeat. The explanation is that one of the inputs is paired with more than one output. Yes, sir?
Oh, you could say no because it does not pass a straight line.
We're going to do that next. Yeah. Whenever I give you a graph. Okay? So, in this case, the input 36 is paired with 6 and negative 6. Each input can only be paired with one output. Alright, let's take a look at number 1 here. And here we're given the set of ordered pairs. Well, we could write that as a table. You guys know how to do this. This is nothing new. We could write it as a mapping. -5, -2, 1, 4. And then the elements of my range are -3, -1, 1, and 3. 5 is paired with 3. -2 is paired with 1. 1 is paired with -1. And 4 is paired with -3. Now, if I had repeating elements of my range, I only need to list them once. This one didn't. But if I did have repeating elements in my range, I'd only have to list them once. We'll look at one of those in just a moment. If I look at the graph, I've got the point here, the point here, the point here, and the point here. And that does lead us to talk about how would we tell if a graph is a function? Yes? Yes.
You just have a straight line and move it from the left side of the graph to the right, and if it doesn't run through 2 points at the same time, it passes.
Okay, so what Sabrina, right?
Yes.
Just described perfectly was the vertical line test. And the vertical line test is used when we have a graphical representation of a function. Like these 4 points that are graphed. So if a vertical line, if any vertical line, not just one, if any vertical line passes through no more than one point, then the relation is a function. So, what she said you would do is you would take your pencil and hold it upright and run it across, and if your vertical line represented by your pencil never passes through more than 1 point at a time, then yes, it is a function. So, we can tell from the set of ordered pairs, yes, that's a function. We can tell from the table, yes, that's a function. We can tell from the mapping, yes, that's a function. And we can tell from the graph, yes, this is a function. So we could have any of those 4 representations of a relation and determine whether or not it's a function. All right, at the bottom of the page, they gave us a mapping, they gave us a graph, they gave us a table. In this first mapping, is the first mapping a function? Yes or no? No. When it's not a function, I don't normally make you define the domain and the range. The domain is always the input, the range is always the output. So if you had to, you could easily write the domain, and the range. When we have these discrete elements, we write them as a set with the braces, just like this. Why is this not as a function? The input, -2, is paired with more than one output. Okay, number 4 is a graphical representation of a relation. So do the vertical line test. Does it ever pass through more than 1 point? So is it a function? Yes. Now, these are not discrete points. This formed a line. It's continuous. And whenever we have a continuous function, when we describe the domain and range, we're going to use what's called interval notation. So this part is probably new, and this is what we'll use all the way through high school. With interval notation, we always start with the least value and always go to the greatest. If we include the point, we have the brackets, and if we do not include the point, we use parentheses. Now, domain is the smallest input value to the largest input value. my x's. What is my smallest x to what is my largest x? It goes from 0 to 4. So domain, we always go from left to right. Domain always goes from left to right. And you always go from your smallest, which would be the one furthest left, to your largest, the one most right. Now range is your y values, your output. And your range is going to go from bottom to top. Yes, ma'am.
Where did that one include period?
Why does that one have the brackets? Because it included the point here, and it included the point here.
The point there's 3.
I was about to say that.
Oh, that's a 3. Thank you. Hard to look at everything from the side. Thank you. All right, now let's do the range, bottom to top. What is the lowest y value? 1 to what is the greatest y value? 4. That's my range. Now, this interval could also be described by a compound inequality. We could say it goes from 0, all the x values are between 0 and 3. We could write this as all the y values go from 1 to 4. You see how these two mean the same thing? This means this, this means this. Yes, ma'am?
How did you get that range again?
The range is the lowest y value. What is the y value here? 1.
Oh,
Up to the highest y value. What is the y value here?
Okay.
4.
Thank you.
Okay, this one. Is this a function? Yes. The domain includes 0, 2, 4, 6, and 8. And we would write it in order. The range includes 4, 6, and 8. And even though the 6 and 8 appear twice, we only list them once in the range. Okay, an answer for yes is always going to be each element of the input is paired with exactly one, or each element of the domain is paired with exactly one element of the range. And on the graph, I guess you could put it passes the vertical line test. That's how we know. Okay, you don't have this yet. I'm coming around as soon as I find where I put them and passing out this worksheet. Here they are. Okay, we're going to start in the middle of this page so we can go over the graphs. And don't put your workbook away because we're not done with it. This just fits in nicely right here. Okay, look at numbers 7, 8, and 9. 7, 8, 9. 7, 8, 9. Decide if 7, 8, and 9 are functions.
Can we put away our workbooks?
No, we're not done. I don't know if I'm going to have my copy. I said, yes. Okay, so is 7 a function? No. It fails the vertical line test. And because it fails the vertical line test, that tells us that there is an element of the domain that is paired with multiple, more than one, elements of the range. Right? Okay. 8. Function. Yes. Okay. I want you to add arrows to the ends of this because I failed to do so. Alright. Domain goes from left to right. And because I put arrows on this end, on the ends, this function goes out that way forever and out that way forever, doesn't it? So it goes from forever left to forever right. Forever left to forever right. What concept do we use in mathematics to talk about forever? Infinity. Okay? So this function, forever left, we describe as negative infinity. And forever right we describe as positive infinity. So the domain of this function goes from negative infinity to positive infinity. Now, a minute ago when we talked about domain and range, I said we'd use the bracket if it includes the point, the parentheses if it does not include. Can we ever get to infinity? Is it an actual number? No. So can we ever include it? No, it's an idea. It's not a number. So that's why we use the parentheses with infinity. Now, let's do range. Range is bottom to top. Bottom to top. This one's going down forever. What's the bottom? Negative infinity. Down forever takes us from negative infinity to the top. Well, this one has a top. It stops right there. What is the y value right there where it stops going up? 4. And it includes that 4. Okay, number 9. Is this a function? Yes? Okay, what is the smallest, most left x value? Because that's where our domain starts. Negative 5?
I'd say 4.
I say negative 8.
It's right here. What is the x value right here?
Oh, that's like.
Okay? Negative 5. Now, with an open circle, does an open circle include the point? No. So I need a parenthesis right there. Now, this is the most left point, isn't it? That's the most left point. What is the x value on this most left point? Excuse me, most right. I said left like 4 times. Meant right. 10. Now, this is a closed circle. Does it include? Yes.
Wait, so. Wait.
So open circle
Okay.
means it does not include, and a closed circle means it does.
Exactly.
Ian wants to know what the point is, if it's included or not.
What do you
Like,
mean?
what is the point that it's included?
What if you were the ordered pair for that point right there? Wouldn't it be like 10, negative 4? So what is the x value of that point that's included? 10. Okay, so domain is your x, range is your y. So let's look at this one. Here's my bottom y, right? Here's my top y. You see how I put those little dash lines in at the bottom of the top? So what's the bottom y right here?
Negative 8.
Negative 8?
Actually, negative 6.
And what's this top y? Positive 8. It's a lot easier to see it on your worksheet than on my screen. Okay. So, last thing I want to talk about today. This ties into something you already know. You already know linear equations. You know how to model them. You know how to write them. You know how to graph them from 8th grade. Okay? All we're doing now is we're thinking about lines as functions. There is only one line that's not a function, and it is the vertical line. The vertical line is the only line that's not a function. It's also the only line that doesn't fit into this form, isn't it? So any other line is a function. A horizontal line is a function. Any type of diagonal line is a function. The only line that's not a function is a vertical line. So, any linear equation gives us a linear function except for vertical. And what we know about linear equations is their slopes are constant. So how could you tell if it's not a linear function? It would not have a constant slope. Okay? Some of you were panicked when you saw the homework. Most of it's really quick. Like, is this a function? Yes or no? Okay? So your homework is the front of the worksheet only, front only, and then the textbook bookwork that's listed on your calendar and is also on the board. Don't forget your phones. There's 3 phones.
What's the homework? That one?